Okay, hello everyone. This is mechanics of materials, and in this video, I'm going to show you the internal force calculation. And internal force calculation, the example is just like I show you before in previous video. We are using the example 7.1. Okay, and in example 7.1 in previous video, I say, okay, we would done if we want to calculate internal force at this section C, we cut the section method, we cut the section on section C, and then we use the CB section to do the calculation and obtain the internal force at a section C, across section C. But now in this video, I'm going to show you, okay, in last video, we use the CB section, and in this video, I will use the AC section to do the same calculation, and we will get the same answer. And also there's some issue I want to talk about. Okay. So we use the AC section to do the calculation. Okay, so I change I switch to another window. Okay, in this problem, I think, okay, A here is a fixed support. Okay, is a fixed support. Okay, and then we use the AC section to do the calculation. And previously we use the CB section. And when you use the CB section, you can ignore everything on the left. Okay, so when we use the CB section to do the calculation, we ignore everything on the left. Okay, and do the calculation. But now, when you use the AC to do the calculation, and then same idea, we ignore everything from the right. Okay, but that doesn't mean using AC section is easier. On the contrary, if you use the AC section to do the calculation, it takes more time, and I'll show you why. Okay, we use the AC section now. Okay, AC section, we still have the distributed loaded. Okay, we still have distributed loaded here. Okay, and here is still at the end A is 300 Newton per meter. Okay, here, and you need to know what's the force intensity at the C section. And in the previous video, we already calculated it's 200 Newton per meter. Okay, and at this section C, okay, we just assume the internal force has the shear force and the normal force, and also there's a internal moment at the C. Okay. Okay, so can we just do the calculation based on this information? No. Okay, because in the AC section we involve the support. Okay, support, and it's a fixed support. And in the previous section, we know if you are the fixed support, there's a reaction from the support. Okay, and the reaction force and reaction moment from the support. And the fixed support, so we'll have AY, AX, and also moment at A. Okay, so if we want to calculate internal force by AC section, you also need to calculate the support reaction from A. You have to. Okay, you have to. Okay, in previously we use CB section because when we use CB section to do the calculation, we ignore everything from AC section, so you don't have to consider the reaction force and reaction moment from the A support, fixed support A. But now if you use AC section, sorry, you have to consider this. Okay, so you'll make calculation harder. First of all, so how to calculate the reaction from A? So how to obtain reaction from A? Okay, you need to do the global ridge body equilibrium. So you have to do the whole ridge body equilibrium calculation for the whole system to obtain the support reaction from A. So you have to do the global ridge body equilibrium. Okay. Okay, so that's why when you use AC section to the calculation will takes much longer. Okay, so but let's start because this the class just show you you still need to do this. Okay, anyway, okay, because you are the first time you learn this course, so you still need to know this. Okay, okay, so we do the global. Okay, we do the global ridge body equilibrium, and then we write the ridge, and then we write down the we do a free body diagram of body of the whole system. Okay, so this is okay. Mm-hmm. Okay, so the whole system we want to do the rich body equilibrium, but okay, when you do the whole rich the whole system rich body global rich body equilibrium. Okay, so this is the force diagram here, but we need to do the simplification. Okay, because this is a distributing load. Okay, so I have to do the simplification. So the simplification, what we will have, what do we have? Okay, here. Okay, same thing here. I'll write it again. Okay, AY, AX, and MA, MA. Okay, and then okay, the resultant force here. Okay, and where is the position of resultant force? Okay, so you have to use what you learn in the simplification of distributed loading. Okay, and in the simplification of this distributed loading, the first of all, you need to calculate the magnitude of resultant force. And in the distributed loading, the resultant force, okay, what is the magnitude resultant force? The magnitude resultant force, okay, is equal to area under the distribution curve, load distribution curve. Okay, here is 300. Okay, point down. Okay, point down. Okay, so and total length is 3.6. Okay, so the area of this curve under of this right triangle is 1 over 2 times 300 times 3.6. Okay, so okay, it's 540 Newton. Okay, it's point down. And where's the position of resultant force? Okay, don't forget in the distributed loading, the position of resultant force is just right at the centroid of this area. Okay, and where's the centroid of this right triangle? I believe the centroid, I think it's close to, I think it's about here. Okay, and what's the distance? And then what's the distance here? Okay, the question mark. Okay, the question mark is just equal to, okay, the centroid of a right triangle. I think, like I said, this should be a common sense in your mechanics of engineering calculation. Okay, it's equal to, so I don't want to explain it anymore. So it's equal to 3.6 divided by 3. It's 1.2. Okay, meter. Okay, so, okay, since the whole system is rich body in each rich body equilibrium, so and it's 2D system, and in 2D system we only have two equation. Okay, we need to use the summation fx equal to 0, summation fy equal to 0. Okay, and the other one is the moment, total moment equal to 0. Okay, okay, total moment equal to 0. And the moment, okay, with the reference point, I think we use the A as a reference point, okay, because we want to find the position of F1, we need to use the A as reference point, okay. So sigma Fx equal to 0, so what do we have? Okay, I think I should, I should write it more, not in messy way. So it's a moment A. Okay, A is here at the end, okay. And as I mentioned, f x equal to 0, so we have x component here, ax, Okay, that's only the X component force in the system, so nothing else. So that's very good. Okay, the total the y component is zero, so we have AY, okay, point up. Okay, and then we have FR point down, and FR is 540 Newton point down, so it's minus 540. Okay, and nothing else. So we solve this out. AY is equal to 540 Newton. Okay, and the total moment at A is equal to zero because at A we still have the moment. A has the reaction moment, so we still have to write this moment out. So we have to write the moment out. So and okay, and A, okay, and AXAY because it's acting at the A point, so they won't create any moment. AX and AY won't create any moment if you use A as reference point. But A this point has another reaction moment, so you still have to write it out. Okay, okay, and FR also create a moment with respect to A. So, okay, the fourth point down, the reference point, first point is A, so it will create a counterclockwise moment. So FR and times the lever arm just right here. Okay, 1.2, and actually it's negative because it's clockwise, so it's negative. Okay, so equal to zero. Okay, so what will we have? We got our MA is equal to FR is okay, 540 times 1.2. So it's 648 Newton times the meter. Okay, it's a moment. Okay, so okay, we got a reaction force and reaction moment from this A point. Okay, do we solve this problem? Not yet. We just figure out what the reaction force and reaction moment at this A point. So we had to put this information back into this this free body AC free body diagram of AC section. Okay. Okay. Let me copy this. Let me copy this. See if I can copy. Okay. Can I paste? 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 Paste. Oh, very good. Ah, okay. Okay, but we still need to do the more, still have to, okay, write it more clear. Okay, we just write down all the information we have. Okay, okay, here's 300, 200, 300, 200 Newton meter. Newton meter. So, and we have reaction force AY is as A, it's 540 Newton, and we also have a reaction moment. Okay, reaction moment 648 Newton times meter at A. Okay, and we also have the okay, normal force, shear force, and the moment at C. Okay. Okay. So okay. So the next step of this the next step of this calculation is okay. Right now the AC section we still have distributed loaded. Okay. So you want to do the rich body equilibrium to calculate VC, NC, and MC. You still have to do the simplification of distributed load again. You have to do the simplification distributed load again. Okay, okay. So it's very annoying. And now the distributed load is become a trapezoid. Okay, it's not right triangle anymore. So it's become a trapezoid. Okay, so that's why. Okay, it's very annoying problem. So many calculations. It become a trapezoid. Okay, and then you do the simplification of this trapezoid. How to do that? Okay, because trapezoid, it's not easy shape, but we can make a when divided the shape into a very simple shape. I draw the purple line here. So here, so let's say, okay, here is will be a FR1, here will FR2. Okay, I decompose this trapezoid into a rectangular and right triangle. Okay, and then we can calculate the resultant force of each simple area. Okay, and also the centroid of and the position of this FR1 and FR2 very simple because right triangle and rectangle we can identify its centroid very easily. Okay, first of all, let's us calculate what is FR1. Okay, FR1 is just area of this right triangle and length is 1.2. Don't forget the information. Okay, so 1 over 2 times 1.2 times, this is 100, don't forget, because this total is 300 and here is 200, so here is 100. So this will be 60, okay, Newton. Okay, so, okay, so FR2, let's see, what's our FR2? Okay, FR2 is 1 point, is the area of this right rectangular, so that times 200, so it equal to 240 Newton. Okay. And so, okay, where is the position of the resultant force? Yeah, for the FR2, very simple, very, very simple. It should be like, it should be here, and here is the half. So here's 0.6. And the central of FR, central position of R1, I think the central is about here. Okay, and what's the distance here? It's very small area. So here, I think I don't have to explain this. It's 0.4. It's 1.2 divided by 3. Yeah, central right triangle. So I said, like I said, it should be a common sense in your mechanics of engineering calculation. Okay, so okay, we have the resultant force and result and position and resultant force, and then yeah, do okay. So this free-body diagram can do the more further simplification. Okay, this will what this will become like this. Sorry, sorry, sorry. Yeah, this takes a lot of time. Okay, so NC should be NC BC MC MC C. Okay, at the point A, okay, reaction force at A, reaction force, sorry, 1 Newton, and the moment MA, so 648 Newton times meter. Okay, and here we have FR1. Okay, let me change it to Pareto. FR1 here. FR1 should be okay. FR1 and it's zero point 0.4 here and FR2 here. Got FR2 here and here is I think here is 0.6. Okay. Okay, so with this information, yeah, we can solve the VC, MC, and NC out. Okay, use the rigid body equilibrium again. Oh my god. Oh my god. Oh my god. That's really that's really hard calculation. So many procedure. Okay, so that's why I use CD section is much easier. If you choose AC section, oh my god. Okay, so we use the rigid body equilibrium again. Whole system is in rigid body equilibrium. So let's we use this equation again because 2D problem. Okay, so x component. What do we have? X component looks like we only have NC has x component. Okay, NC equal to 0. Okay, okay, so we are and y component is also to 0. Y component, be careful. We have one y component force here, 400 or 540. And we have FR1, FR2 point down. Okay, be careful. FR1, FR2 point down. So minus 60 and minus 240. And final one, we have shear force at the C section. So assume it's point up, okay, equal to 0. Okay, so the shear force at C will equal to minus hmm, minus 240 Newton. Yeah, I think you will feel it. Okay, because in previous video we kept using the CB section. The shear force at the C section is 200 is positive 200 and 240, but now we get the minus 240. Why? Okay, I'll explain this later. Yeah, because the answer here is positive, but why we have a negative answer here? It doesn't mean you calculated wrong. I'll explain it later. Okay, so the final one is okay. The final one is the total moment of the system is 0. So where we should choose a reference point. Hmm, we should choose a reference point. A or C. A or C to a reference point. A or C should be a reference point. If we choose A, what will happen? If we choose the moment at A, what will happen? Moment at A, okay, we see 140A, and here, if we choose A as reference point, this FR1 will create a clockwise rotation. So we will minus FR1 is 60 times 0.4. FR2 also clockwise, so it's also negative because it's a clockwise. So from 40 times 0.6. And the whole system, the moment is 0, so we have a MC here. MC equal to 0. Okay. Mm, okay, let me see. Okay, 640A minus 6 times 0.4 times 0.6. Oh, not 100% correct. Okay, but if you choose a reference point A, hmm, okay, so I think the answer is wrong but the A, we choose reference point A. Hmm, reference point A is equal to 0. Let me see. Okay, so in the class, I choose a reference point C and we get the answer. But why we choose a reference point A, we don't get the answer. That's really strange. That's really strange. Hmm. Okay. Okay, let's start with we use choose C. Okay, maybe there's some issue here, but okay, we follow the decision on class. Okay, if you choose the C as the reference point, choose C as reference point. Okay, still have 64A. And if we see a reference point, and the reference point is C, that's 540 Newton. This force will create a moment, okay? It will create a clockwise. So it will become, so that's 1.2 minus. And the FR1 and FR2 also create a moment for the counterclockwise. So it will become FR1 60 times 0, it becomes 0.8 because the labor arm is 1.2 minus 0.4 and counterclockwise and plus FR2 240 times 0.6 and plus MC equal to 0. I think this will get the answer, but my question is if you choose reference point A or reference point C, they should have the same answer. But why? Why I didn't get the same answer? Well, anyway, okay, let's figure this out. Okay, MC, okay, MC, okay, MC 6吧. Okay, it's cancel out. Okay, so it will become So it will become minus 190 Newton times dot meter. Okay. So in previous video, if we use a CB section, what answer we have? In previous video, the answer we have is 240 Newton, and here is 190 Newton times meter. So you will see if we use the AC section to calculate the reaction for the internal force at this C point, will have the magnitude is the same, but we have a reverse sign. Okay, and I just say that doesn't mean your calculation is wrong. It's just because yeah, you must get a reverse answer if you calculate you calculate from the right and calculate from the left. You will get a reverse answer. The reason is because the whole system is in rigid body equilibrium. So left hand side and right hand side must be have reverse sign. Okay, I can show this picture for you. Okay, okay, I show this picture. Okay, so okay, no, here. Okay, if I cut here and cut here, your material cut here. Okay, I cut here. If I have a right hand side, left hand side is up, the left hand side must be going down. Okay, because these two will be cancelled out to each other because the whole system is at the equilibrium. Okay, same thing if I cut this section and left hand side is pointing down, okay, and the right hand side must be pointing up. Whole system it must be equilibrium. And also, what happened the moment it's also happened to the moment. Okay, if I cut a section here, cut a section on the left hand side, cut a section on the right hand side. If the moment at left hand side is counterclockwise, and right hand side must be clockwise. Left hand side counterclockwise. Left hand side must be clockwise. So the whole system will be balanced. Okay, so because the whole system is in balance at the rigid body equilibrium, so the result, your internal force calculated from the left hand side and right hand side, there must be a reverse sign. Okay, so that's why we will have a different kind of looks like we have different answer from previous video, but actually it's the same. Right, it's the same. Okay, let me draw finish this. Okay, so that's just one thing I need to tell you. So this issue will keep happening in this course. Okay, that calculate right hand side, left hand side will have the different not different answer. You have reverse sign because rigid body, the whole system is a rigid body equilibrium. Okay, so my last question is, yeah, about minutes ago, I chose A as a reference point, but I cannot get the same answer. It's very strange. But it seems looks like we have to choose a C as a reference point to get the answer. Hmm. But I'll figure this out. Okay, but the answer now is correct. Okay, this question is too long. I just start a video here. Okay, I start video here, and then see you in another video. Bye bye.